The notes are fairly short, but there is some stuff underneath that which you'll need to do as well. So in the notes, the way I've done it is I've done the notes here on the right-hand side. And that's it. That's all the notes there are. All right? And I even wrote real big. So there's not much to write. But on the left-hand side, what I did was I put the examples. And for the examples, there are 4 examples, and there are 4 short little videos that just step through the equations. Okay? So after you've taken the notes, then go through and watch the little videos and fill in all of the information on these examples so that you can do it here on the worksheet. On the worksheet, you're going to show all of your work along with your units. Okay? So make sure that you're showing your work and your units. So that means do it here too. Now before we start, I wanted to show you a couple of things about this equation in particular. So we are familiar with this equation. FG is equal to big G M1 M2 divided by the distance squared, or sometimes it's written as like the radius squared when we're talking about the radius of a planet and something on the planet. The distance between their 2 centers is pretty much the radius of the planet. But so sometimes you see that as r squared underneath. But this is the equation for the force of gravity. And this is the equation for the electric force. Notice the similarities. They are the same. We have 2 objects with mass 1 and mass 2. Over here we have 2 objects with charge 1 and charge 2. They're proportional to the, inversely proportional to the square of the distance, meaning the distance squared is in the denominator, just like it is over here. And they have some sort of constant. So for gravity, the constant is big G, the gravitational constant, which is a very, very small number. 6.67 times 10 to the negative 11. Okay, so very small. And then over here we have the Coulomb constant, which is a big number, 9 times 10 to the 9th. Okay, so big number, small number. But other than that, these are the same equation. Now there's one important thing to notice that's a little different, and I don't usually even bother to write it, but these 2 lines right here, what do these 2 lines mean in math?
Absolute values.
Yeah, absolute value. So it means take the magnitude of this number, the positive value. Don't worry about whether it's positive or negative. And there's a reason for that. Okay? So if we look at direction, let's assume that we're looking at a number line. And in English and other writing systems that write from left to right, when we're looking at a number line, we've got 0 in the middle, and then we have negative numbers or positive numbers going off this way, and we have negative numbers going off this way, right? So positive and negative. So when we're looking at a force, it makes sense that there should be a positive and a negative, except for one thing, and that's Newton's third law. Newton's third law says what? Who can remember?
Every action has an equal opposite.
Yes, very good. Every action has an equal and opposite reaction. So if I have 2 charged objects, plus and minus, if I multiply a plus and a minus together, I would get a minus, wouldn't I? So a minus would indicate on a number line which direction? That way. Okay? These 2 charges are attracted to each other because they're opposite. What direction is the force on the charges? They're attracted. So one of them is this way and one of them is this way. So what is the positive negative thing about? It's about nothing. Okay? What if these 2 were both positive? They would repel. Which direction would the charges be? That way. Yeah. So it doesn't make sense to say that the force has a positive or a negative. The direction of the force depends on whether or not it's repulsive or attractive and which one of the 2 particles you're looking at. It could be that way or that way, couldn't it? The only thing that we know for sure about these 2 is one specific thing. I drew 2 forces here, and I drew 2 forces here. But how many forces are there here? How many? 1. Why did I only write 1? Why does this number not give me 2? because of Newton's third law again, which was what? Every action has an equal and opposite reaction. And that applies in all cases. So for instance, let's suppose that I have a big charge, +3, and I have a little charge, -1. They're attracted to each other, aren't they? Because one's positive and one's negative. Is the force on this one more than the force on this one? We might think so, but what does Newton's law say? Newton's third law? Equal and opposite. So whatever the force is on one, it's going to be the same on the other. Because the force doesn't matter about what this charge is, and it doesn't care about what this charge is. It cares about what the product of the two multiplied together is. Okay? So the force on these two is always going to be the same. Now, if one of them is heavier than the other, maybe it doesn't move as fast because it can't accelerate because it's heavy. Okay? That's the same as when we talk about gravity. So for instance, I'm standing on the Earth. I'm small. The Earth is big. Which one has more gravitational force between me and the Earth? And the answer is neither one. It's exactly the same. The Earth is pulling me down with about 235 pounds of force, and I am lifting the entire Earth up with about 235 pounds of force because the forces are equal and opposite. Now, me being pulled down by 235 pounds of force makes a big difference, particularly if I trip, okay, because I don't have that much mass, so I'm going to accelerate down pretty fast. But the Earth has a huge amount of mass. So if I trip and fall, does it fall up to meet me on my way down? Yes, it does. But does it fall fast? No, because the Earth is so big that 235 pounds of force is nothing to the Earth, right? But the force is the same. And the reason for that is because you need two objects to have a force. Always. Always. Okay? Yesterday we learned that we can have a field with one object. If we have a charged object, it makes an electric field around it. And the Earth has a gravitational field around it. But a force only exists between two objects. Mass 1 and mass 2. And then there's only one force because they're equal and opposite. Okay? So the Earth and the Moon, which one has a bigger gravitational field? The Earth. But what about the force between the two? The Earth is big and the Moon is small. Maybe the Earth has a bigger force. No, it's equal. The force of the Moon pulling on the Earth and the Earth pulling on the Moon has to be equal because those are the two objects in that system I defined to be those two, and they produce one force. So it's the same, exactly the same with charges. Okay? The only difference with between charges and gravity for math purposes is the fact that for charges we have both attraction and repulsion, whereas with gravity it's always just attraction. Okay? And of course the numbers are much bigger because this constant is way bigger than this constant. Okay? So two charged particles, if I put two charged particles here with even a very small charge, I can actually measure the force between them. But two small particles with mass, it's very hard to measure gravity that small. Is there gravity between this pin and this pin? Of course. Anything that has mass has gravity. And if I floated these out in space away from anything else, eventually the gravity would make them come together. It might take 100 years because the force is so small, okay? But it exists. But with charges are many, many billions and trillions of times stronger, the force, than with gravity. Gravity is actually the weakest force of the universe. We can tell because, look, we can lift this thing up against the force of the whole Earth, right? Well, the force of the Earth and because it takes two objects to make the force. All right, any questions? All right, so go on and do the notes, then step through the video to fill in the examples, and then do the worksheet. Okay, the worksheet will be due when you come in tomorrow. We'll grade it in class. and then you'll turn it into me. Make sure on the worksheet that you're showing your work with the units. Okay. All right, let's get to it.